Thanks, Gloria, for the introduction and also for the previous talks. So what I'm going to do here is to also go back to very basics about virtual reality. I've understood that some of the students following the Cassini meeting are completely new in the field. So I will be very general in some aspects. And we have divided this talk in two parts. I will do a first presentation, and my colleague Gwenael will do a live demonstration at the end of this talk in about half an hour, so that you will be able to see some real-time application of virtual reality. So, and we are working in the Laboratory of Planetology in Nantes, in France, and we've been doing some virtual reality for the Plan Map project led by Padova. So, what I am going to do is to speak about some very basics about why we are caring about doing some virtual reality. And I will give you some background and also make the difference between augmented and virtual reality. Sometimes it's not clear for people. I will show some example of how we compute the 3D models in order to study both the Earth, the Moon, or Mars. And then I will end with some discussion about these test cases and use cases, in particular using online web platforms such as Sketchfab, or using custom applications that we have been working on. So just to start with, why do we care about virtual reality? In fact, I guess that a lot of people have seen this week that we have a lot of data to process, and in particular, we have several terabytes of orbital images taken in particular on the case of Mars and the Moon, with images which have a resolution which can be as low as 25 centimeters per pixel on Mars and 40 centimeters per pixel on the Moon. So this is really, really precise. And we also have the ability to compute digital elevation models to have the shape of the planetary surfaces. And we also can compute, the summer school one was also nice for that. We also have the possibility to compute a lot of thematic maps. So maps of composition, thermal inertia, any kind of parameters that we can also use to complement the high resolution imagery. So we have a bunch of orbiters, but we also have landers and in particular rovers on Mars. And with this rover, in particular, we've been working in Nantes within the Curiosity team. We have several hundreds of thousands of images to process. So we can use these images to recreate partly the surface of Mars. And what we need is tools in order to ingest these images in a seamless, I would say, a seamless way in order to give the users the possibility to work in the images or at least to manage the amount of data. So why also do we care, scientifically speaking, about the immersion? If you take this image, which is a 360 panorama taken by Curiosity, you see that it is really hard to understand what are the sizes of the boulders, also the distances of the boulders, and what are the relationship between the different units. And this is even worse on the Moon, where you have no atmosphere and where you have, well, all the astronauts say that it is very difficult to say, okay, this boulder is very far or and small, or it is close and big. So this is a problem. On Earth, we have less problem with same images because our brain is trained to recognize features such as cars, trees, houses, roads. So in this case, my brain understands that there is only one road here. If I go back to the Martian case before, my brain does not understand that this unit is linked to the other unit here. So the immersion will help you to bridge the gap between these problems. And from my experience, the best things that you get with immersion is the sense of scales, distances, and also relationship between the morphological units, and in particular when you are dealing with layers, sedimentary layers, for example, in several environments. I provided some colleagues the possibility to test VR headsets, and I had very often this kind of feedbacks, people saying, oh, I didn't realize that this outcrop was so big. And even in case where the same scientist was studying the same outcrop, it has been studying the same outcrop for months before on a traditional screen. So when you go to VR, you see something much more realistically than on a flat screen. So just to be clear of what we are talking about, for those who are not up to date about these techniques. First domain is the augmented reality. In this case, you are using a device, smartphone, or a cell phone, or a tablet, which will add information on your environment. So in the case you see on the lower left here, you're using an iPad, and on the iPad, you see a model, 3D model of the Curiosity rover just in front of you on the table here. So if you have not already done it, I would suggest that you download the Spacecraft 3D application. It's free, and you can select any kind of planetary probe, and you will have your favorite planetary probe just in front of you, so that you can zoom in, look at the instrument, and see how it is made of. So it's very interesting for outreach. We are also using augmented reality for science, and in particular, in the Curiosity team, we are using this kind of headset. If you are looking to my webcam, you can see how it looks like. So this is a quite expensive headset, $3,000. But the very interesting thing is that you put it on your head, and through the glasses here, you will see a small square, which is just in front of you, where you will see, in particular in this application, you will see the outcrops, which are just in front of the Curiosity rover. So the application is updated day by day. So as soon as images come back on Earth, we are able, with this HoloLens headset, we are able to see the ground and to walk at full scale on the ground to see the rocks and the boulder which are around the rover. So it helps us to do the operations, to select the targets that we want to investigate the following day, for example. So it is something that is very useful both for operations on a day-by-day basis, but also for science. If you want to go back to a specific site to analyze an outcrop, then you can do it with your headset. And it also has a social functionality. If you create a meeting room, then you can invite your colleagues. You see your colleagues in forms of avatars wandering into the environments, and you can discuss with them directly as if you were on the field. So it's a very nice application. And you can also use this HoloLens for instrumentation design. What you see in this video is the spacecraft called Dragonfly, which is the next mission to Titan, supposed to be launched in 2026 and to arrive in 2034. So it's basically the same kind as spacecraft as Curiosity, but you remove the wheels and you put rotor wings in order to fly in the atmosphere of Titan. And for the design of this spacecraft, engineers are using the HoloLens, so augmented reality, in order to build the instruments and to optimize several parts of the instruments. So that was augmented reality. Now I switch to virtual reality, which means that you have a complete immersion. So you can do it by two ways. First way is to use what we call a cave system. The cave system is an environment which can be as big as your meeting room, where you use at least 4 video projectors, can be up to 16 3D video projectors, which project on the 3 walls plus the ground. So by doing this, the user simply needs to put glasses, active glasses on his head, and you have a controller. Here I'm using an Xbox game controller to move into the virtual environment. So we've built a cave, a custom cave in our lab in Nantes, and this is how it looks like. So it's quite convenient because you are not completely closed in a headset. You only wear some light glasses and you can see your landscape in a fully immersive way. The cost can be very high, up to several millions if you want to have a professional setup. So the other way to do the immersion is to use VR headset, and this is what I think is the biggest revolution we had during these last few years. So just to make you some historical facts, how did it start? It started with a small company called Oculus in 2012, which make a development kit called Oculus Rift DK1. This is what I brought in the lab. It is just here. And we had a lot of fun with that, just to see some 360 panoramas, for example, or to start doing some VR. But with this headset, the pixels are very big. Your set is not tracked, so it means that if you are moving like this, the image does not change, so your brain gets some sickness, motion troubles. So it's not very efficient. We had some second test of headsets made with a pizza box. Very simple. You put here your cell phone, and then you have a very cheap headset. I would not recommend this either, because you will also have some motion sickness. You can have it in plastic. Also, I would say forget this one. And what is a big revolution is the first availability of technologically mature headsets, which arrived in 2016 only. So if you have not tried VR before, or if you have tried VR with what I said previously, forget it. You have to try it with either the HTC Vive or the Oculus Rift consumer version headsets. This is where you will feel more comfortable with no motion sickness anymore. So the revolution is still ongoing. On each year, there is a new headset. The one I would recommend is this one, the Quest 2, which is just available for the community since a few months only, and it is less and less costly. This one costs only 250 euros. So it's more and more affordable for the general public, and technologically speaking, this one is very nice. And HTC Vive is very nice. So the hardware is very important, and this is what we have been using in Nantes in our lab for, I would say, 7 years now. And both of these systems are very useful. I just need to mention the last point is that the Oculus Quest can be used as a standalone headset. You don't need to use a PC. With this one, you can have only the headset with light application. And if you want, you can also connect your headset to a PC with a cable, and then you will benefit from the high power capabilities of your graphic card to do something much more demanding. So that was the point about the hardware. And now I will discuss a little bit about the how we are doing the 3D models and how we are doing this kind of applications. So first, one important thing is the creation of 3D worlds. So for those who were there this morning, it was quite widely discussed already. What you need is at least a pair of 2 images taken from different viewing angles. So if we take orbital images, then you need at least 2 viewing angles to be able to compute a digital elevation model that you can compute with specific softwares, such as the socket set software or the AIMS stereo pipeline software. And once you have created your digital elevation model, you can drop the texture of your image on the digital elevation model, and then you get your 3D world. So you need to integrate this into a graphical engine in order to render in real time the lighting conditions and be able to move in this system. And you can also ingest in situ images. So if you take images either by yourself on the ground on Earth with your cell phone or digital camera, or if you are using rovers to take your pictures, or even if you are using old pictures taken by the astronauts on the moon, you can do 3D models with the images, and by integrating all the view taken at different angles of your environments. So what we are using for this is what Gwenael explained this morning, and also Luca, for those who were there. It's called the structure for motion photogrammetry technique, and it is more and more used in geosciences. So in this case, we can simply take all our set of data taken on ground or with your drone or with your spacecraft for the planets, with the overlapping images, the overlapping areas in the images, then you will find matching points that we call sparse point cloud. Then from this matching point, you will be able to derive a more dense set of matching points. And by linking your points with triangles, then you will obtain what we call a 3D mesh. So basically a 3D model of your environment. And then you simply have to reproject the texture, so the pictures, the photographies, in each face of your 3D model, and you are done with your 3D modeling. So this can be done at different levels of accuracy. And for example, if I remember what Francesco Soro said in the previous talk, it can be very important to be very accurate in your reproductions. So if you are doing a model, it can be very detailed, but in this case, it will mean that you will have a file which will be big. So you need a big graphic card in order to be able to manipulate in real time your model. So you will have some issues about the optimization of your 3D dataset. So you can not do everything at full scale if you are using terabytes of data. So you have to find a kind of trade-off between the accuracy of what you want to see, scientifically speaking, on your outcrop or your rock modeling or environment modeling. So you need to find the good trade-off between finding the right scientific information and also having the right size of your models in terms of computer performances. So in the case of Curiosity, we are doing this with a set of 5 cameras. And Curiosity, you see here a picture of the remote sensing mast of Curiosity. So we have basically a set of cameras which are not fully optimized for 3D. We have the NavCam cameras, which are the black and white cameras with the widest field of view. You see an example on the right side here. So these cameras have a very nice advantage, is that it is a stereoscopic pair. So each time we are taking images, we are taking the 2 eyes, and with this stereoscopic pair, it's quite easy to retrieve a 3D model. But what we are most interested in is that is the color imager coming from the what we call the Mastcam 30 and the Mastcam 100 cameras. On the right side, you can see the respective field of views of these color cameras. And you see that the field of view is more tiny, 3 times tiny, for each camera. So it means that if you want to do stereo with this set of images, it becomes more tricky because you have stereo effects, but you are mixing cameras taking images with very, very different focal lengths. So still, it's doable, and you can end up with complete models after some, I would say, some effort in order to integrate all this. And just to finish, to mention the cameras that we have on board Curiosity, there is a camera called RMI, which is the image of the ChemCam instrument just here. It is the instrument we are working on in Nantes. And the RMI is a camera with the smallest field of view. If you see on my screen, it's very small. It's a small black dot that is just here. And even with this camera, we are able to do 3D models of outcrops that have been imaged doing mosaics of very distant outcrops. So it's doable, but it's not easy. So just to recall, something that we have been doing in the framework of the Plan Map project, it's a work done on the part of the Curiosity Traverse. It's called the Kimberley outcrop. So this is a place where we used 2,000 images taken by Curiosity, both with the navigation camera and with the science color cameras. So in this place, once integrated, you see how the different steps are done here. The steps consist in finding where the images have been taken. Then by using the matching points between all overlaps, then we are able to produce a 3D point cloud here. And then the 3D point cloud can be wrapped with pictures, so with mosaics of the images in order to obtain a 3D model which is as accurate as possible of this area covering the Kimberley region. What you see in blue here is the position of the cameras. So basically, it means that the rover came from here, spent some time at this place here doing 3D 360 imaging. Then he moved a little bit here. And each time Curiosity is moving, the meter is taking a picture. Then he's moved, and again a meter takes another picture with an overlap between all of these pictures. So it is very good for us because it allows to bridge the gap between several parts where he's staying to do some analysis. And in particular, if you look here, he stayed several days in order to perform a drill here. We will discuss this later. Perform a drill here and take a lot of images, a lot of analysis also with a bunch of instruments, such as laser and so on. So as the rover is, when the rover is staying a long time in a place, it is good for us for 3D because we have time to take a lot of images. And the more images we have, the more precise will be the 3D reconstructions. And in particular, we spent some time looking at the drill hole here, which was imaged by the microscope of Curiosity. And with the microscopic imager, which is on top of the remote sensing, the robotic arm, we are also able to take images from different viewing angles. So we were able to do a 3D model of the drill hole here in order to have a very precise 3D reconstruction of the environment at this place. Basically, the resolution of this imager called Mali is up to 14 microns per pixel. So it means that in specific places, you can do a 3D model of a rock or a piece of a rock which have less than a few hundred microns of accuracy. So one thing which is also very exciting is the future. And I would say the future in 2 weeks, because the next rover, which is called Perseverance, will hopefully arrive on Mars on the 18th of February, so in 2 weeks now. And Perseverance is equipped with 23 cameras, so more than Curiosity. Curiosity had only 17 cameras. And what is very, very cool is that the navigation cameras of Perseverance, which are his two eyes, will be stereo cameras again, but they will be in color instead of black and white. And they will be 20 megapixel cameras instead of 1 megapixel cameras for Curiosity. So it will produce an exceptional data set for 3D reconstruction. And in addition to that, you have the Mascad Z instrument, which is the same set of color images as the one we had on Curiosity, except that it is a zoomable telelens. So we can have a pair of wide angle at 30 millimeters of focal, but we also can have a pair of tele images taken at 100 millimeter of focal. So to do the 3D reconstruction, it will be okay to have a pair of images taken at the same focal length. So it should be very efficient. Hopefully, as I said here, you have to cross your fingers if you want to play with these images in the future. So something which is important is also how do you render your productions. So I just want to start with the mention of the online web platforms, and in particular, one which we have been using quite a lot so far is the Sketchfab platform. So for those who don't know Sketchfab, it's a site where you can very easily upload and sometimes download 3D models. So we have a site that we open with for our lab at the LPG. So you can visit this site here, or the one that we used for the plan map project. And you see a snapshot here of some of the models that we have uploaded on Sketchfab. If you select a model, then you can see the model with your traditional computer screen. That's very easy to do, first way to do it. But you also have here some options, and in particular, you have an option here to activate the virtual reality rendering of your model. So if you have a headset connected to your PC, and a PC compatible with virtual reality, you will be able to see the model directly in virtual reality. So you will have the model in front of you. You will be able to change the scale of the model. So you will be able to explore the environment simply by using this online platform. So this is very user-friendly, very easy to use, but at the same time, you have limited functionalities. So you have very limited interactions with the model. So it's good for a first experience, but it's not very complete. So Sketchfab is also interesting if you want to do some augmented reality. If you take your cell phone and you download the Sketchfab application, then you will be able, by going to the Sketchfab application, you will be able to see your models in 3D, so in augmented reality. So you will be able to have your model in your hand, or to simply walk around the 3D model that you have uploaded. So again, it can be very nice to discuss with your colleagues, for example, having the outcome just in front of you in your hand, or to show it to students, or even to analyze it yourself with your for your science. So it is something which is quite convenient and quite easy to use. If you want to go one step further, then you need to do something much more, I would say, complicated. And I have a small video here to show a project that I've been working on in the framework of the plan map project. So here, the idea is to use an engine in order to render in real time the planetary surfaces. So in this case, I'm using images taken by either orbiters. So often we are using very high resolution images, depending on the size of the area that we want to investigate. And we can drop whatever kind of information we want, either the imagery, but we can drop a geomorphological map if we want, or we can drop a false color image or a spectral color image information. And as you are in VR, the idea is that you are free to move on this place and you are free to select your viewpoint. So again, it will help your brain to understand the real characteristic of this place. And as Francesco said just before on Loredana, I think that it is very useful if you want to train an astronaut or a pilot. It is very helpful to use this kind of simulation in order to simulate what they will see if they have the chance to go there in their life. So we have been also working on another application which had an objective, which was to do science, real science, and in particular, in this case, the objective was to do geological measurements in virtual reality. So again, that's a work which has been done in the framework of the PLANMAP project. And this application has been done by our colleagues working at the VR2 Planets company. So they developed for this an application where we were able, that was the objective, we were able to immerse ourselves in the Martian environment. So in this case, we used, again, satellite images to recreate the place, merged with images taken by the rover directly, the Curiosity rover directly on the ground. And by matching the two data sets very accurately, this application gives the user the possibility to take geological measurements, such as distances, angles, deep strike. So all these kind of measurements that a geologist wants to do. So you have a small video here showing the application with somebody in action, and Gwenael is going to show you, to make you a live demonstration right after this introductory talk. So you see, just briefly in this video, that you have a bunch of tools here on your trackpad, and you can zoom in, zoom out to select the scale at which you want to work on the place. You see the squares here in white. It is the position where Curiosity was when it took all the pictures. And with your remote controller, you are able to place points directly on the outcrops, and you are able to measure the distances and also the angles of each of the layers. So this is something which is often key to interpretation of the area in order to decide if the area has been, for example, formed in a sedimentary environment. Was it a lake? Was it a dune field, a fossilized dune field? Was it a river? And if it was a river, did the flow come from here or did it come from here? This is the kind of information you can derive from the measurements you will have here. So this application has been put in the PLANMAP cloud here. So at this address, you can pick up the application and you can experience it by yourself. Again, it has been done as a scientific tool first. So the ergonomy is what it is. The objective is really to do the science measurements here. So to just finish this part of my introduction, I will also mention another possibility to do some VR, and it's the use of the Steam platform. Steam is a platform that is used very widely by the gamers, by the gaming aficionados, and we have been using Steam in order to recreate some planetology environment, and in particular, we used the Kimberley outcrop model in order to produce a scene where people are able to meet. So we are able to meet people in VR and to discuss directly with people coming from anywhere in the world. This scene is online on a public site. So the address is here. And we know that some of the students following this talk have their headset at home. So we send to those having a headset, we sent some instruction before, which were to have a Steam account, to install the Steam VR application and to subscribe to the Kimberley outcrop scene, which is the one you see here on the left part, and to send a friend request to LPG_Caravaca, which is my colleague sitting in the next room here. And in 10 or 15 minutes, looking to my watch, in let's say 15 minutes, we will ask you to, for those who have a headset, we will ask you to join and join Gwenael in this live meeting room. So this is something which is very convenient. I should mention that in this Steam application, there is no scientific tools, so no way to do accurate scientific measurements. This was part of the previous application as I showed you. So all these tools are, I would say, complementary. So here is just a snapshot. We made a test with our colleague in Padova yesterday, and it is a snapshot of our session in Steam, where we were so able to join together. We were only four, but we were able to join and to discuss some of the aspects of doing geology on Mars. And just for fun also, I just wanted to mention, it's a tribute to our colleagues of Padova. So we had our very first meeting in Padova for the PLAMAP project. And I have some free time to do some sightseeing in Padova. And I spent half an hour in the Capella Scroveni, which is a very nice place. And with my cell phone, I have time enough to make a 3D model of the Capella. And this is a place that we can also visit now on Steam, just to have some, I would say, some place. And the only drawback is that we cannot take a cup of real cup of coffee together there, but it can be used for breaks and as a, I would say, some application outside of planetology. So, and it's also an echo of the question that was asked before about archaeology use of the VR. So VR is, I would say, something extraordinary for both planetology, of course, but also for archaeology and art. So just I want to mention that, in my point of view, the most important thing with VR is to give you the sense of the scales. So what size is this outcrop or rock? What size is this environment, this site? And what is the relationship between the morphological layers or units I'm seeing here and there? So of course, that's very useful for science. I'm convinced of that. Also for teaching, I'm also convinced that in several years, a lot of geology course will be done directly in VR. And it's also complementary of doing a real field trip. And my personal opinion is that if you are going to do a field trip somewhere, it can be nice to do it first in VR so that you know before going approximately what will be the experience. Then you go on the field. And when you come back in your lab or in your school, then you can go back in virtual environment and make the link between what you saw in reality in the field and what you are seeing back on or retrieving in the VR headset. So I think it's very complementary of both. So it opens clearly new fields of applications. And in my last slide here, before going, giving the floor to Gwenael for live demonstrations. So I've indicated again some addresses of our Sketchfab main account, also the stream VR file scene of Kimberley, and also the VR application with the tools, the geological tools, which is here in this repository of PLAMAP here. And I've added some references of papers that you might find interesting in order to go deeper into this topic. And now, before I just wanted to acknowledge our colleagues of PLAMAP for organizing all this. And I also wanted to acknowledge my colleagues of VR2Planets for providing this very nice application with tools, measurement tools, and I think it's time to leave the floor to Gwenael. I'm seeing in my webcam that he is ready now. So that Gwenael will continue the demonstration, but giving you in live an overview of what he is doing, both in the application with the VR tools, measurement tools, and then he will switch to Steam VR so that we will be able to meet everybody who has a headset at home and who has registered to this experience, hybrid experience. So thanks for your attention. And I didn't have the conversation window open, so I was not able to follow if people said something during my live talk here. So I try just to stop sharing my screen so that Gwenael will be able to share his screen. Okay, it's done now. So I will leave the floor to Gwenael.
Okay, hi again, everyone. Good afternoon. Can you hear me and see my screen?
Yes, me.
Okay, perfect. So, hi again, and I would like to welcome you on Mars. Actually, in virtual reality, but yet it's a pretty nice view. So, I will take a few minutes to give you a tour of these geological tools for virtual reality measurement. So we have developed in collaboration with VR2 Planet. So as you can see here, I am hovering a little reproduction of only a little part of the gate crater. Stephane said it a little bit earlier. Reproducing very large amount of data is very complicated due to the giga or terabytes of data. And if we would like to reproduce the entire gate crater, it would be a little bit difficult for our computer. So here we have only reproduced an area which is about 3 kilometers square. So a square of 3 by 3 kilometers, representing the region around the Kimberley area, the outcrop I talked about this morning during my digital outcrop modeling presentation. So first of all, to start with, I remember that there was a little bit earlier, minutes ago, a question about how we could use orbital data to complement the digital outcrop modeling in virtual reality. Well, actually, what we are seeing at the moment is the virtual reality reproduction, which is based on actual orbital data. This is a high-rise ortho image, which is grayscale, and that has been draped onto a high-rise digital elevation model. And this is the base data that we are using to provide the context, to provide a regional reproduction of our virtual environment. So here in orange, you can see the reproduced traverse of the Curiosity rover. So Curiosity came from this corner here in the northeast part of the region. It drives on this area during about a year, and then exited the area here on the southwestern corner. So as you can see, obviously, orbital data are very useful for us to complement the digital outcrop models, which are obviously very highly accurate, but not big enough to reproduce the entire region. So one of the first functionalities I wanted to show you is that, like a GIS, like QGIS or ArcMap, we can switch the layer and we can use the virtual environment to display several types of information. So here I am displaying the high-rise ortho image in grayscale, but I can very easily show the geomorphological map that has been done by the Curiosity team prior to the mission, and I can observe the different outcropping orbital facies anywhere in the region. So here you can see that I am moving around the map, just like I would be with a very small model. And easily I can change altitude and changing the scale also to have a better look, closer to the surface, closer to the real scale at the environment. So here you can recognize the digital outcrop model of Kimberley that I showed this morning, and that has been replaced as the true scale in this actual position over the orbital imagery from IRISE. So I can see here that a variety of terrains has been described for Kimberley, which are the striated unit in blue, the homuncular plains in green, for example, or the bright rugged terrain in yellow. But I can again switch the layer and show here an IRISE ortho image, but this time in color. This is my preferred version of the layering because it is obviously in color and give a more realistic look and a more immersive environment to have a regional context. And for the little fun fact, here, this little bright spot, you can see, is curiosity. Curiosity has been spied by IRISE and taken in photo several times, and here we have chosen to put the photo of curiosity at Kimberley for this virtual environment reproduction. You can also see that the orange line representing the traverse of the rover is well in line with the actual tracks left by curiosity in the Martian dust. So now we are moving on to the real floor, or at least the floor reproduced in virtual reality. And you can see on my screen that the scale is diminishing towards 1/5, 1/4, 1/2, and to the actual true scale. So here, welcome again to Kimberley. I am actually walking into the Kimberley environment as it was reconstructed using photogrammetry. So here, obviously, I can move around the terrain. I can go everywhere that I want, and more particularly, if I want to observe the outcropping rocks that are featured at Kimberley, it is very easy for me to just move around, go there, and to have a very close look at the different sandstones that are composing this formation. So basically, virtual reality is very useful here to have a very detailed and close look to the several geological formations, but the enhanced version of this simple exploration is the ability to take measurements. And that's why we developed this application in the first place for the PlanMap project, is that we have the ability to take measurements. So here on my left controller, you can see that I have several different possibilities, several different buttons, which represent the distance, angle, or dip and strike measurement tools. So I'm going to make a little demonstration on how to measure this section. Well, exactly like I would do on the real field on Earth with my ruler or my laser distance meter. I can simply choose the vertical measurement tool, place one point at the base of the formation, place a second point, let's say here on this marker bed, and I am able to read the actual thickness of this little interval, which is here 71 centimeters. So if I want to measure this interval at a different place, I can do the same. I'm still placing one point at the bottom, one point at the top, and here I can read that I have about 72 centimeters, which is fairly the same measurement. So this tool is obviously very interesting, very powerful to measure distances at a close scale, but I can also make measurements at a larger scale. And this is particularly interesting to be able to change scale between the actual close true scale at the outcrop, but also to have a larger look at the regional environment to be able to make measurements or correlation at a larger scale. For example, here, if I want to measure the distance between the Mount Remarkable here, which is the main butte at Kimberley, and the two other buttes a little further north, well, I can place one point on Mount Remarkable, one point on Mount Joseph, and I can see that these two buttes are separated by about 100 meters. The same between Mount Joseph and Christine, which are separated by about 46 meters. So these tools are very powerful and very useful to be able to make actual measurements, the same measurement we would do if we were actually able to go on the terrain. But here, obviously, Mars is very far, it's very complicated to go there, and for the moment, it is the only way that we have to do the fieldwork. But simulated fieldwork in a virtual reality environment doesn't mean that it is completely wrong. As my colleague said earlier, we are using specific data that has been controlled for their accuracy, for their realism, and so the measurements that I am doing here in virtual reality are obviously accurate and exact, and we could observe exactly the same using the photographies taken by Curiosity. One little trick to check on this is simply to control the scale given by the tracks of the rover. The wheels of Curiosity are about 40 centimeters wide, and this specific width has been chosen to be able to have a scale. So here, if I am focusing on the tracks left by Curiosity, I can make a measurement, and you will see that I have about 42 centimeters, which is well within the error margin of the model. And as you can see, the tracks have been left in the sand, so we have a little bit of error indeed. But 42 centimeter track left by a 40 centimeter wide wheel, it is very accurate and very exact. So here you have seen the measurement tools. Now I will showcase you the angle measurement tools, because it can be very useful to take measure of angles also. For example, a very simple measurement is what is the angle of the movement made by Curiosity. I can see here two sets of tracks. Well, I can place one point, the tip of the angle, and I am opening the angle, and I can see that Curiosity turns about 96 degrees to join the base of the Mount Remarkable. So as you can see, the method to make a measurement between an angle or a distance is very simple. I have only to place points anywhere in the environment, and then all the computation and calculation are made by the application regarding the actual shape of the 3D model, the 3D reconstruction. Another very powerful tool which is interesting us is the ability to compute dip and strikes. It is very difficult to reconstruct the dip and strikes of lineations or beds in the 2D views or the 360 panoramas sent by the rover or other probes. But in 3D and virtual reality, it becomes obviously much simpler because we have the actual 3D shape. And here we have a very interesting tool that is able to compute best fit planes with 3 or many points. And if, for example, I want to observe the dip and strike of this marker bed that I am selecting as indicating at the moment with my controller, well, I have only to place several points, so on the outcropping bed, and you can see that a plane, a best fit plane, is appearing. So the most points you are putting, obviously, the greatest will be the accuracy. And here, if I'm following this bed, I can see that I have a plane striking 154 from the north and near the horizontal. What is very interesting with this kind of tool, I said it a little earlier, is that you can switch from very close range toward a more regional view. And this is particularly interesting here if I want to, for example, project this plane, to do so and see if this very specific bed is intersecting other geomorphological features to try to make some regional correlation. So here I can see that this specific plane at this given altitude is also crossing this butte or those little methods. So I am able to make regional correlation that will have been very difficult to do in 2D view or only in your favorite GIS software. So, to finish with this little demonstration of tools, you can see on my controller that I have this panel with the distance, angle, and plane measurement that I just showcased. But you have also another line which are the, let's say, classical GeoGIS measurements, the exact same measurement tools you will have on your pocket in the field, which are simply your compass. Obviously, what is a GeoGIS without a compass? But also a clinometer, so that we are able to observe dips of any feature. Once again, what is a GeoGIS without a clinometer? And also a little altimeter, GPS-like, which gives you the exact coordinate, east, northing meter, and the altitude of each point. And here we are seeing that we are exactly on this point at minus 4,480 meters below the geological reference of Mars. So that will be all for this little presentation of the geological tools. I highly encourage you to download this application on the PlasMap website, and if you have the occasion, obviously, if you have the possibility to wear virtual reality headset, to try these tools and to make yourself at ease with them and, well, just do a little bit of field work on Mars.
So now I think that Gwenael will be shifting to Steam in order to try to meet people. So if some of you have a headset, I saw some question in the chat. You will not be able to do it with a cell phone. A cell phone, even put in a cardboard, is not enough. You need a real VR headset in order to do this experience. So I would suggest, I don't know what you have, but an Oculus Rift or Oculus Quest or HTC Vive. So at least a real virtual reality headset. And also, Gwenael is going to connect to Steam. Now I'm seeing is still in the VR tool. So what we will be doing is that he will launch the scene. And once the scene is launched, then he will be able to invite those who send a friend invitation to Gwenael just before. He will be able, maybe, Gwenael, do you hear me? No, okay.
Yes, I can.
Okay. Okay, super.
Can you hear me again?
Yes, it's coming. Yeah, cool. Somebody is already there.
Okay, perfect. I am seeing that some of the students are coming to Mars. Hello?
So
perfect.
So just to be clear, we are doing this in real time. It's the first time we did it. So everybody connected here is connected in real time. And something we have not tried is to check how many people, what is the maximum of people we can invite. So it might maybe crash at some point if we are too many people in the same place. But we'll see how it goes. Gwenael, I leave the floor to you.
Okay, so welcome everyone. I don't know if people in the steam room can hear me. If you can, yes? Oh, okay, perfect. So welcome again. It's a very nice pleasure to welcome you on this little scene. So as you can see that this Kimberley outcrop is the very same model that we have used for the geological measurement. But here it is, let's say, a much simpler representation. We have only the digital outcrop model, a little bit of IRAS orbital imagery to make the background, so that's why we are able to see the relief all around us, and obviously the magnificent view of the Mount Sharp to give us a little bit of context. And we have also added this 3D mesh of the Curiosity rover at the real scale. So it is very simple to check if it is a real scale. When I am putting my hand here, it is about 2 meters, and 2 meters is the height of the remote sensing mast. So here you cannot change the scale, but you can obviously experience the environment as if you were there actually in real scale. So here we can have a little trick. So the Curiosity rover stood exactly in this position about 6 years ago in 2014. And you can see that the Curiosity made a little drill, which is called the Winjana drill. Here, if you can look where I am showing you with my little lightsaber, you can see the drill made by Curiosity. And if you are looking even closer, as I am doing right now, you can also observe little, very tiny, less than a millimeter wide black dots, which are the marks left by the ChemCam laser. ChemCam, to make its observation of the geochemical composition of the rock, is shooting a very powerful infrared laser beam. And when this laser hits the rock, it transforms it in plasma, which is used to observe the geochemical composition. And it left very tiny black dots where the rock has been burnt. So you can see those very little dots on this micro digital outcrop model. So we see if other persons are able to join us. I am inviting as many people as I can. And for the time being, well, we can observe, for example, the very nice sedimentary structures. I know there is a very, very beautiful example of trough cross stratification. Here it is. So for the people liking sedimentary structures like me, here you have a very, very beautiful, very large trough cross stratification. It is very interesting to observe these sedimentary structures because it can give us information about the power of the river that deposited these sediments. And here, having a trough cross stratification obviously indicates us that the river that once flew here at Kimberley was very powerful, with a direction of flowing towards the northeast. So as I said earlier with the demonstration of the geological measurement tools, we have here the tracks left by Curiosity. Hello, I see a newcomer. And these tracks are the demonstration that Curiosity was here. It is a very similar sightseeing that the famous footprint of Neil Armstrong on the moon. Here we have the footprint of Curiosity. So for those who are a little curious, a little further in this direction, you can see that I have placed several points that will bring you to a bright spot on the texture of the terrain. This bright spot is the image of Curiosity taken by the IRISE instrument in orbit. So that is the the image of Curiosity spied from orbit that I showed you a little earlier. And it is used to show you also that why it is important for us to have 3D models and reconstruction using photos taken on the ground and not only from orbit. As you can see, from orbit here, the terrain it's like a soup of pixels. It is not very accurate. It's hard to see details. And yet, this is the most detailed imagery we have. It is highlighted with the resolution of 25 centimeters by pixel. So that's why it's very important for us to have ground-based data and such models made by photos taken by Curiosity to be able to observe things at a very lower level. So if we are going just here, let's ignore it, you can see also that Mars is still an active planet. Here you have several subtle structures that have been made by maybe gullies, maybe sand flowing, dry flowing. Also, we don't know exactly when it happens. It is recent in Mars history, but on Mars, recent can mean several tens or hundreds of thousands of years. So we don't know when it happened, but it happened, and we can see that sand is still flowing on the ground of Mars. Finally, another interesting part of this outcrop is when we are looking toward the east. As you can see here, you are seeing very coarse sets of northwest dipping strata. It is part of the striated unit. It is called striated unit because from orbit we are seeing this terrain as striated. And we don't know yet exactly what it means in terms of depositional settings, but we think that it might be some dunes left by a river flowing there before the time this part of the outcrop was deposited. So why it is so important to understand if it was before, at the same time, or after? Simply because, as you can see with the dust, the regolith, it is very difficult to see the contact between the formations. And here, being able to see this outcrop in 3 dimensions at true scale in VR allows us to observe the exact placement of this formation and to try to understand their stratigraphic relationships and to see if this specific part of the outcrop is under, at the same level, or over the stratigraphic sediment, the sedimentary series that we are seeing just 35 meters ago. So obviously, if you have any questions, whether it is here on the Steam scene or obviously on the Zoom meeting in the Cassini Zoom, I can answer your questions. There is absolutely no problem of that. So as you can see on my screen, what I am doing now is I am just drawing a little line drawing. It is the same thing I will do on Illustrator, on my screen on Illustrator. But here I am doing it in 3D, and this is very interesting because we can see the actual 3D configuration of those sedimentary structures.
Gwenael, how many participants are in?
For the moment, we are 1, 2, 3, 4. We are 5 in the virtual environment.
Okay. Can the other join?
I have here actually 4 guests.
Okay.
So for those who are here this morning for my presentation about digital outcrop modeling, you can have here firsthand a little taste of the different issues that we are experiencing in making digital outcrop modeling. Is that if you are looking here very close to the river, we have a very beautiful reproduction of the sedimentary structure. But if we are getting a little higher on the butte, you can see that the textures become a little more blurry, a little more deformed. That's because the point of view was more remote, because Curiosity, as you can see, was in this very position. So here I am 5, 6 meters away from Curiosity, so it was very much difficult to have better image, and that's why we have some limitations on the ability to make accurate digital outcrop modeling in remote position. So that illustrates the little balance that I was trying to explain this morning, that we need to have a lot of accurate images, but on the farther area, we can still experience some trouble in recreating accurate representation of the terrain. But fortunately, in 5, 6, 10 years, we will be able to go there for ourselves, so it will be much easier. So I am seeing that our colleague from Padova just joining. Hello? Sure. Mm-hmm. Yes. Yeah, it was co-registered using Cloud Compare. In Cloud Compare, there is a function that allows you to co-register and to check the alignment a little bit like if you are doing georeferencing under ArcMap. You are selecting several points, and then you can do a broad, not very precise co-registration, and then you have an automatic function that helps you having a better co-registration. But we have done this so at least a little bit manually. And then to be sure to have a very high accuracy and to be very correct, we have also checked under the we have checked against the high-rise model that was already registered against the molar altitude model. So we have made two different checks to be sure to have the correct scaling and also the correct position. The difference we are seeing, just for example, follow me here.
Gwenael?
The difference in altitude that we are seeing between the two models is only due to the grading, because here we have a model that is precise at the sub-centimeter scale, but high-rise digital elevation model is precise at 1 meter. Yes, Stephane?
Annie is saying in the chat that she's trying to join, but she cannot do it. Do you check? Can you check if she's in the friend list?
Yes, she is. I can see she is online.
Okay.
And I have sent an invite.
Okay. So maybe she should be joining soon.
You're welcome. Ciao. So as you can see, a little field trip on Mars is something very playful, and this is a functionality, a social functionality enabled by the SteamVR platform. It can be a very interesting tool also, the SteamVR platform, to make some serious game for some animation, some serious game, and also a place together to observe at real scale a specific model. Here, obviously, we have the Kimberley outcrop, but we have made also several tests of other outcrops on Mars or on Earth. And it is interesting for us to check this in a very easy way to see if our outcrop models are accurate enough to work on them.
I'm saying, Gwenael, that it is 4:15, just to let you know, as you might be on another time scale or schedule. So
No problem. So for everyone who are here in the Steam room, thank you for getting me. I will have to leave to prepare for the next activity. I hope you enjoyed the visit on Mars, and feel free to come back every time you want. It's free, it's open to everyone. Thank you, and bye-bye.
your webcam is freezed, Gwenael.
Yes, I have seen this. Okay, so this was a little demonstration of the two applications that we wanted to show you today. The first was obviously a more serious application, really dedicated to making geological accurate measurements on a replicated, reconstructed digital outcrop model and a virtual environment representing the accurate depiction of the actual surface of Mars in a place that Curiosity visited some years ago. And the second, as you saw, was a little more playful, a little more social experience meant together or to just enjoy the view and to be able to share with the public for outreach activities, but also to just discuss the relief, discuss the structure we are seeing, and a very great way to encourage the use of the virtual reality.
In fact, we were in the same lab.